Welcome to Breadboarding. This is video 47 in the Breadboard 8088 PC series, and this is the second part of building a CGA video controller. So the Breadboard PC project started with a very early version of an 8088 breadboard computer with a 7-segment display and keypad. Then we went on to build a basic floppy disk PC and booted early versions of MS-DOS. And as part of this phase, what we've been doing is adding an IDE disk controller and hard disk, getting MS-DOS to boot off the hard disk. And the next stage is actually building a color graphics adapter capable of running early versions of Windows. Now in the previous video, which I include the link for up the top here, so this was introducing the CGA video card and some of the background information around it. So I'm not going to repeat most of that information here. This is a photograph from -0degrees.net of one of the early CGA cards, and this was based around the Motorola 6845 cathode ray tube controller chip. The characters were based in hard-coded ROM, read-only memory. It had 16K of dynamic video RAM. It had a composite video output which could be sent to a composite monitor or via an RF modulator to a TV, and it also then had a CGA video output which was digital TTL levels. From the previous video we summarised some of the key points. So CGA has a hard-coded ROM-based fonts and 16K of video RAM. We are going to use a VGA compatible digital analog converter palette chip, so this makes it easier for driving the VGA video output for LCD monitors. Now the original CGA had 640 by 200 pixels, and the character display was made up by 8 pixels by 8 pixels characters at around 60 Hz refresh rate, and in fact this was the 14.3 MHz dot clock, and the horizontal sync frequency is about 15.7 kHz. Now this is where the original 4.77 MHz clock for the IBM PC came from, in that is the 14.3 MHz divided by 3. So the 80 by 25 column display uses 1 byte for each character and 1 byte for the attributes or colour, so that means it uses about 4,000 bytes. In order to do the graphics with 200 rows on the screen, the CRTC 6845 is only capable of doing a maximum of about 127 rows. So in fact what happens is the CRTC is configured for 100 rows, and then one of the raster address lines, so this determines which line of a particular character is going to be shown at this point in time, is used to toggle between the lower 8K of RAM and the upper 8K of RAM. So this means that it can then do the 200 rows. So we're going to be doing 640 pixels across the screen by 200 lines in 2 color, so that will use 16,000 bytes. And then there's a 4 color mode that uses 320 pixels across by 200 lines with 2 bits per pixel. That gives us 4 colors. We're producing sort of CGA output, but it's actually VGA compatible. So it's software compatible with CGA, but the physical output will actually work with more modern monitors and video capture cards. So the output we're going to be providing is 640 pixels by 400 lines rather than 200 lines. We're still going to be using the 8x8 font initially, but this is going to be a frequency of 70 Hz, and because of the VGA dot clock frequency of 25.175 MHz and the horizontal sync frequency of 31.5 kHz, we're going to actually need to double scan these lines. This basically means that for every row we're actually outputting the same information for the 2 rows, and that basically means we ignore the raster address 0 and we only use raster address 1 upwards instead. Now, this is a diagram that I showed in the previous video, and this in fact comes from the technical guide for the CGA graphics adapter. So this is the IBM Colour Graphics monitor adapter. The links will be in the description below. And we covered a lot of the content of this in the earlier video, so this is the diagram that I'm basing this on, and there's a lot of the tables for the various configuration options on this. But the key thing that we're interested here is that in the back of the technical guide we've actually got the schematics for the CGA card, so we've got 6 sheets there. And what I'm going to do is to go through those in summary, and then we'll also be looking at a KiCad schematic for the original CGA card, which someone has kindly made available on GitHub. So when we're looking at the design here, we've got the video RAM here, we've got address latches and buffers really going from the processor and from the CRTC going over here. We have the CRTC chip. Now in fact we're going to be making use of an Hitachi device which is compatible with the 6845, but it does have a few extra features and it does actually work at a slightly higher frequency that will work at VGA frequencies. There's some palette and overscan information. The overscan's not that important just because the LCD monitors we're going to be driving don't really make use of the overscan area. So this was for cathode ray tube where the colours in the top of the bottom of the screen could be controlled. The mode control controls the various video modes. The timing is going to be changed from the CGA timing to VGA timing, so there's quite a few changes in this area. And what this will also mean is we won't really be able to use some of the CGA specific test utilities that rely on very accurate timings, because the timings here will be quite different from CGA, although the output will be compatible. So in getting the data out of the video RAM, there's two data latches. One feeds the character generator ROM, and that determines which of the 255 characters are actually shown. And then the other latch, when in text mode, this actually handles, in fact, you'll see here I've added this green line in here. So in text mode, this other attribute latch effectively determines what the foreground and background colors which are being shown. And then the alpha serializer, this is a shift register that basically takes each line of the character based on the raster address. So there's 8 raster addresses for each character, and this will actually serialize the dots, and then the color encoder works out what red, green, blue and intensity signal we need to use. Now this is going to be using our VGA color palette chip that will require a little bit of redesign in this area. Now the original CGA card would actually produce composite color for feeding into a composite monitor or through a TV RF modulator would drive an NTSC television. Now we're not going to bother with those because that complicates the design, and really the VGA compatible output here will make things much simpler. Then we've got the interface to the processor data bus has an input buffer and an output latch. So the latch just means that we can read the data and let the processor read in its own time without interfering as much with the operation of the video controller circuit. So I'm going to be going through the schematics now, and I'll make also reference to the KiCad as well once we've gone through that. So this is the first page, CGA sheet 1 of 6, and what we've got here is the cathode ray tube controller chip. I've highlighted in red where we're not really going to be using these signals. Orange, there's a specific issue that we need to be aware of. Now in this particular case there's a few minor complications. So what you'll notice here is that the address multiplex latch is here, that in fact the address A1 is the first one that goes on here, and then A0 is actually in fact occurs much lower down here. So I'm not entirely sure what the reason for that is. I suspect it might be something to do with the refreshing of the dynamic RAM or something like that. But what this means is we just need to be a little bit wary of changes like this. We can also see here that the clock input to the CRTC comes from an inverted character clock here. And then down the bottom here, there's also another bit where we were talking about the use of the raster address 0 to switch between the lower 8K and upper 8K. Then this logic down here basically says that when we're doing graphics, then we're actually getting this line is coming from RA0 here, and when it's in alphanumeric mode, then in fact it comes from the MA12, which is the line output from the CRTC here, MA12. So depending which mode we're in, we're either taking it from MA12 or we're taking it from the raster address. Now in fact, because we want to double scan our lines from 200 up to 400, we're not going to be using RA0, we're going to be using RA1. So effectively by ignoring RA0, then we get the same line twice. Then over here we've got the 16K of video RAM. Now I believe the original video RAM on this board, based on the part number here, the 21185 4, I think it was 400 nanosecond access time. Rather than using dynamic RAM, we're going to simplify the design a lot by using a 32K static RAM chip, and it just so happens that these 32K static RAM chips are very fast. They're 15 nanosecond access time, and that allows us to simplify the design somewhat, because basically within 1 pixel clock cycle it is actually possible to address and read the RAM. And then at the top here there's a bit of logic which has kind of strayed from some of the other sheets, and this basically handles in the alpha mode the dot output and takes into account things like the cursor blinking, the character generator dots, whether or not you've got a blink clock, the cursor, and various other things. So this basically outputs whether or not we expect to show foreground or background color when we're in the text modes. So this next one's a little bit busier, but I'm just going to cover the high level stuff. So we have a status register here. This is how the PC can query whether we're in a screen blanking period, so can defer doing updates to the screen until we're not actually updating the output to the screen. There's a data input and output buffers and latches to the CPU. We have the attribute latch and the character latch. So the character latch drives the character generator ROM and the alpha serializer that produces the bits to determine when we're showing the various pixels of the characters. And the attribute latch, when in text mode, in fact goes through and controls the color output. So this color encoder down here, this is how we determine what the foreground and background colors are. And then this video output latch produces the red, green, blue and intensity signals, and uses a latch here to synchronize the signals so there aren't any differences in the timing. A lot of this is very similar to the monochrome display adapter design that we've already produced earlier in the project, and in fact that design was also capable of producing color output. Where this differs is when in graphics mode, then in fact these two graphics serializers take the output from the video RAM and actually produces a C0 and C1 color graphics bits, and then these are used to determine what the colors are used here. Now there's also a color register here, so this color register provides a color selection information, and the overscan RGB information and background intensity information is actually used down here to determine which colors are going to be sent out to the video output here. And the color encoder down here, there are two multiplexer lines, MUX A and MUX B, and these control whether we're doing foreground text, background text, whether we're using the graphics or the graphics background, graphics overscan. So sheet 3, the timing generating control. This is quite complex and I'm not going to go into much detail on this. I'm not really going to bother too much about this because this was very much tied up with the CGA timing and dynamic RAM refresh. So there's a lot of stuff here which is not really necessary, and we're going to really rely more on the design that we had for the monochrome display adapter because that was already working with VGA quite nicely. But we do have down here the video RAM address decodes. This decodes a 16K RAM into this block of RAM. So this is in fact I think a 32K block, but it starts at B8000, and then the 16K block will be repeated twice in that address range. What we might be able to do later is look at using the full 32K of the RAM, and then in the MCGA stage of the project you might actually look at changing that to a full 64K of RAM to produce some higher resolution graphics modes. Then we've got the IO port address decoding. So this decodes the CRTC and the various status, color and mode control ports, and those are in the 3D0, 3DF range, and in fact we're using D4 to DA I think is used. There are some areas, so things like the light pen, we're not going to bother using light pen because it won't work with the LCD monitors anyway. And then there is a similar circuit to the original MDA card, has a divider to take the vertical sync frequency and divide that to produce the character blinking and the cursor blinking frequencies. So again, a lot of the logic up here is all to do with the dynamic RAM timing, the RAS and CAS lines which drive the various blocks of the dynamic RAM. A lot of this output here is video control logic, so we are going to need to worry about some of this, but it's probably going to be easier to look at the KiCad schematics for this because it's a lot easier to trace where things are going from. But we do also have the control port down here. So control port is used to control which video mode we have. And in fact, this is the summary of the mode control register information from the earlier video. And you can see here that based on these bits, bit 0 to bit 5, then you can see that different video modes will have different combinations of these bits. So the key thing really is in text mode, then this bit 1 is 0, and in the graphics mode it's set to 1. In the text mode, when we've got bit 0 set, then it's the 80 by 25. When it's set to 0, then we've got 40 by 25. So that's really how we select between the 40 by 25 and 80 by 25. And then there's also a black and white mode bit as well, which determines whether we're outputting colour or we're going to output in black and white. And we'll need to make sure we set up some palette control information for our VGA palette to actually allow us to have both colour and grayscale output there. And then in the graphics mode down the bottom, we've got the 320 by 200 black and white, 320 by 200 with 4 colour graphics, and then we've got our 640 by 200 high res, just black and white graphics. And I believe the foreground and background can be specified in the color adjuster. We'll have to check that in a bit. Then sheet 5, a lot of this is related to producing the color composite generator. So this is producing the chromium signal needed to drive the composite output. And there's also various circuits here to do with modifying the horizontal sync and vertical sync signals so that they're more TV compatible. Now again, we don't need to worry about that because we're producing VGA compatible outputs. We don't really need to worry about the manipulation of that to allow the composite color to work properly. So this will simplify it a bit. There's just a little bit at the top here which is to do with delaying some of these signals by 1 or 2 characters in the character clock. And so this is similar to what we've done in the MDA, and the Hitachi chip is able to configure the delays for some of these signals actually in register configuration rather than needing some hardware. So we may not need all of these bits here. Then finally, the original design had a buffer to send the output to the CGA TTL monitor inputs. We're going to be using VGA, which produces an analog 0 to 0.7 volt output, which is VGA compatible. So we're going to be using the VGA palette chip in this area. Then finally, the bus interface here, there's no composite video, we can drop that. We're not worrying about the light pen. There is a bidirectional data buffer to the main bus, so I'm going to be putting in a buffer for the card because I have run into some problems with too many chips on the main CPU data bus. So we're going to be making use of this CPU data bus, and there is a data gate control here that controls the enabling of this buffer. So if you now have a look at the KiCad diagram, this basically ties back to these diagrams. So I'm just going to go back to the first of these diagrams and we're going to go into KiCad. So this schematic is available at the following URL, and I'll put this URL in the description below. HKZ Lab has kindly put this up here, and I've gone through this and it seems to be a pretty accurate reflection. This has actually produced, I think, a working PCB of a CGA card, so I think this certainly seems to work. And so what I've done with this is gone into this, and what I have done is simplified it. So where there are bits which I'm not using, then I have taken things out. So you can see here, this is the alpha dot output logic, and it's quite nice here in that there's labels and a lot of these things, so we can actually use the tracing options and things. For example, if we look at the character clock there, we can pick up where the character clock is coming from in other diagrams. And down the bottom here, we've got our graphics mode is raster address 0, alpha mode uses MA12. So in the second sheet, this is where we've got the various latches, the character generator and the alpha serializer, and this are the graphics serializer, shift register, and the multiplexer, which is actually producing the color output. So in trying to actually work out what's going on, then it's a lot easier to trace things in these KiCad schematics than it was on the original diagrams. Then this is the clock generation circuit. Now again, we're not going to worry too much about the clock generation circuit here because we already have a working one from the monochrome display adapter which will produce the right timing signals. And then there's the blink and cursor clock there, and then the I/O port address decoding and the video RAM address decoding. I think it's switched the other way around from the original diagram. So if you look at the original diagram, I think the video was in the middle and the I/O was at the bottom, whereas the other way around here. And then you can see here that I highlighted the character clock. You can see here that we've got the character clock highlighted in here, so you can see things come in here. And in fact, we have two clock signals that we use for the character clock going into the CRTC 6845. There's a high resolution clock, so this originally was running at about 1.7 megahertz and the low clock at about 880, 890. However, this will be running at about 3.1 megahertz for VGA and about 1.5 megahertz. So this is the 40 character wide and this is the 80 character wide. Now a lot of the signals here for the multiplexer A and multiplexer B are a lot easier to actually see what's going on here than it was in the other one. So if we have any problems that we're trying to diagnose, then this KiCad will be a lot easier to diagnose and work out what's going on compared to the original schematics in the IBM documentation. And then the output, I've taken a lot of the composite color generation out of here, and in fact the H-sync and V-sync delay circuits we don't need to worry about either, so we can probably take those out. As I've said already, that this flip-flops here which are used to delay some of the horizontal sync, vertical sync, cursor and display enable signals, these can be delayed by the Hitachi 6845 CRTC. Then finally I've taken out the connectors and things which are not necessary. So this KiCad schematic is, if you want to actually understand how the CGA adapter works, then I would recommend you try and understand this rather than the original IBM documentation. And from what I've found, it's pretty accurate. I haven't found any mistakes in this, and given this generates a PCB for CGA compatible card, then I've got no reason to think that it wouldn't be otherwise. So that's a review of the design from the original IBM documentation and the KiCad copy. What I'm going to do now is to break the video there, and in the next video what I'm going to be doing is going through the KiCad diagram and start to lay out the CGA board and start to build out the CGA graphics adapter. If you don't want to miss out on future videos, please hit subscribe, and if you can hit like if you found the content interesting. It just helps to make the videos available to a wide number of people. Thanks for watching.